I started recording, and I will save it and host it. I have to see where I can realistically host it, but I will host it somewhere, maybe on Twitch or on YouTube, maybe. Who knows? I have to figure out. But I'll. It's now recording. Thanks for reminding me. That would have been hilarious. I just hope you can reach me in chat. Can I have this make sounds? Oh well, I just have to pay attention. Oh, that would be great if I had some way to reach you guys, because I think the other people who are in chat do not, or who are watching the stream, do not have an ability to communicate with me. And it would be great if you did. So again, for those people, if you have me on LinkedIn, you can reach me through LinkedIn chat, and I can see those messages as well. I'll find some public chat room. If someone has a suggestion for a public chat room, you can also let me know. Oh, I'm so bad with these windows. Where did I put it? Did I close it again? All right, and I think I should start. It's almost 10 over. For the one person who is in chat, are you okay with doing the inverted F antenna? Or did you have maybe something else that you want to talk about? Yes, okay, great. So I'll put the, let's see, I've checked. So I have it here in the top right. I hope you can see it. If you can't, let me know. This is the thing that I'm going to model. So for the one person, I'll call you Paul. Do you have any experience with Python and or EM simulations per se? Because then I know approximately where to start. While you answer, I'm going to sort, I'm just going to start with the modeling. So I have a Python script open here. I have, let's see if I have the interpreter set. So I am going to sort of assume that you guys know how to install Python and how to run it. Okay, great. So I'm not going to go into details into that. There's a lot of good source material, and honestly, ChatGPT and other chatbots are really good at teaching the basics. So if you have emerge installed through pip install emerge, something very limited. Okay, gotcha. So the first thing we'll do, I'll just give I'll just assume basic programming and get some sort of Python specific things that might be a little bit weird. And if you have any questions or anything that I'm doing that you're like, why is this happening? Please let me know. So first line, import emerge SEM. So for anyone, this SEM basically renames emerge SEM because I'm too lazy to type emerge completely every time. So that's why I do it this way. And what I really like to do if I set up a simulation is define some variables, like millimeter being 0.001 and gigahertz you can even do is 1 to the 9th. This is just so that if you type in dimensions, you can do sort of like dimension is 5 millimeters. So 5 times millimeters, because everything in emerge is in SI units, not freedom units. So again, we're modeling this inverted F antenna. So I'll just quickly make it a little bit bigger, see if I still have it open somewhere. To really guide you through. So there's quite some dimensions here. I'll have this open on another screen on my computer to reference it and see what it is. In this case, if I look at this, there's a lot of rectangular areas. So I'm not going to use the PCB design feature that I've implemented, maybe only for this sort of feed line diagonal bit here, because I have to make a 45-degree bend. This is just going to be typing a lot of rectangles and relative coordinates. So these sizes here are fairly small. So what I did is I took some time to just type them out myself already, because that will save me some time here. So I'll just paste those here. So these are the dimensions in the document. And then I've also selected the material here. Well, it's FR4, just as a reminder for me. we might need some tweaking. So regarding materials, so very quickly, in most programming language, you can define your own data types, which we call classes. And so in Emerge, there is the material class. So, and then in em.lib, you have a whole bunch of materials. So if you type in FR4 here in the modern IDE, you'll see DL-FR4. And if you're like, okay, what is this? You can control, I probably have to do Alt click, and it will take you to the source code of that. And you can see here all these materials that I've added. And be very careful because a lot of these are just, I sort of abused AI to extract them from this very gnarly source code website table. So I hope there's no copy paste errors in here. I still have to check them somewhat, but there are quite a lot. So this is just some definition of variables. So let's start designing this thing. So the first thing we have to do is, if you want to use Emerge, is to make a simulation object. And a simulation object is sort of your home base that collects all the things that are going on, all the geometries that you're making, setting your boundary conditions, etc. They're all inside the simulation thing. So we're going to do sim is, I'm just going to call it sim because it's short, em, which is the Emerge library, dot simulation. And if we type a name here, this name is fairly irrelevant. If you save a file or load it, it will use this name to generate file names. So our sim, our model, inverted F. There you go. You can set the log level here, so how much information you want to have prompted here in the terminal. I'll keep that default. There's really not much to do here. So next step is we start modeling. And so again, I hope if you guys can confirm if you can see this inverted F antenna in the top right corner. I'm not gonna have it in screen because I think that's gonna be pretty crowded. I might make it a little bit bigger. I think that could work, and you don't have to see the terminal at this point. So I might do it like this, just so we can see it. Awesome. ODB is really cool. Oh, OBS, what is it? That's cool software. So I think, as far as I'm concerned, but if I see this, I'm just gonna have to start somewhere. So it's pretty convenient for yourself to define some point that you're gonna call 0, 0. And so I'm gonna put it in the XY plane because I have convenient functions for making rectangles in the XY plane. And I'm just gonna pick this, this point here, which you can't see what I'm pointing at, but it's basically, wait, I'm gonna show you here. It's gonna be right this point here. And I'm gonna set that as 0, 0. So I have this on my other screen to zoom in because the letters are fairly small. Can I zoom in, please? So first thing, I'm just gonna make some blocks here to just start going. The first one is this sort of L7 block. So I'm going to go, just give them random names, em.geo.xi plates. Then the width is L7. The height is H2, and the position is minus L7, comma 0, comma 0. So now we made this XY plate is basically a rectangle in the XY coordinate system itself. So it's z equals 0. So what we can do now is sim.view. So this is sort of the generic thing where you want to say, I want to see what I did. We could just run the script and see that in this GMSH window that we have our geometry. So before anything is meshed, I don't have a way yet to make a fancy plot. So I'm just using the GUI that comes with GMSH. So this is this first block that you see. Oh, my mouse is gone. It's at the bottom. So let's make this, add this wider feed thing. We're going to go block 2, em.geo.xy plate. This is going to be L7. I might rename this plus L4 plus L3. Height H3. This can get pretty tedious, but you just have to go for it. Take the time, and it will reward itself in the end. Height is H2, 0. There we go. You just run it to see. There we go. It feels sometimes like this is going to take forever, but it's actually not that bad usually. I'm also surprised at how quickly things can go. em.geo.xy plate. We're going to go L3. H3 plus, oh god, oh, it's just H1 minus H2. Is it? It's H1 plus W1 minus H2. Position is the same. It actually starts as overlapping, but it's fine. It's the same here. There we go. I'm cool with this. The next one, we're gonna go to 4, XY plate, L1. Oh, let's do the first one, this one first, L3. L4 plus L5. Oh my god, they didn't make this dimension? No way. Oh my god. L4 plus L7 minus L6. I hate this. Why did they do this to me? The height is going to be H4, and then the position is going to be, again, minus L7 minus L4 minus, we'll do it like this. Plus L7. I think this should be it. Height is H2 plus H3 plus, oh my god, I hate this. H5 plus H6 plus H7, I should rename this probably. 0, let's see if I have this in the correct place. Again, if anyone has questions, please ask them somewhere. I can see them, no, we're still going good. This looks good. We can move on. The last block. 5 is XY plate. L2, W1. Position is minus L, so this is easy, minus L6. Then H2 plus H3 plus, oh, this is just H1. Much easier. There we go. Almost there. 2 more, I think. Only 2 more. Plate. This one is going to be the bottom block, which is L7 and H6. Then it's going to be at minus L7 and H2 plus H3 plus H5. 0. Yes. Block 7 is here. Now, some people might look at this and go, why would you program this? It's so much easier to draw. And it's, well, if you have the final dimensions, it's easier to just draw with a GUI. But if you don't and you want to tune and change parameters, this is actually can be much easier. It takes some time at the beginning, but you just got to be patient, and having that parameterization available to you is, in my opinion, very recommended. So why didn't they make this with exclusive? The last one, H7, position is minus L7 plus L5, H2 plus H3 plus H5 plus H6, 0. Let's see if we have more people in here. 1 more people. So again, for the one person who just joined, if you can't reach me in Twitch chat, you can reach me on LinkedIn. I do have it open. I might not get the messages as quickly, but best would be either Discord or Twitch chat. So I think this is sort of it. If we look at these side by side, right? I have this structure, so I have to make this feet structure and then the 2 ground planes. So let me make those ground planes. First, the left one. Ground left is here. So this would be, it's actually not that defined. How wide should I make this? Let's try. I don't know. Width ground left and width ground right. I don't know, these are maybe way too small. To try to make it look a little bit like the example. Let's see. L. And then we're going to make it L ground is millimeters. I'm just starting with something. And then it's 0. This is the right one. Oh yeah, I have to make this gap first. And then it's actually not that bad. This may be a little bit bigger. This may be a little bit bigger. And then this is displaced by L8 plus W2 plus something like this. It's not actually a dimension that is provided in the example, so maybe it doesn't even matter. There we go. I think that looks fine. So now this final trace, am I going to make an entire, yes. So for this trace routing of this piece that's left here, I'm just going to use the PCB class, m.geo.pcb. All right, thickness doesn't really matter. It's the thickness unit. We'll do unit thickness divide. So the thickness, so everything in the PCB class is expressed in its own unit. In this case, I'm going to use the units millimeters, so the thickness should just divide by millimeters to make it work. Material, I'm just going to set it material as. I'm just going to use it for the trace. Normally I can do much more, and you can see in the examples what you can do with the PCB class, but for me it's just to make this line because it's not that convenient. For multi-point geometry. Yeah, you can make polygons. So there's em.geo.xi polygon. So this is essentially a class that allows you to provide a set of points, but then you can also say generate points by a parametric line. You can do extend. And then what you have is essentially a polygon defined in some XY plane. So it's not yet geometry, then you can embed it into 3D space by doing geo. So you're going to make a geometry out of it. You give it coordinate system, and then it will sort of put itself into the XY axis of that coordinate system. And the coordinate system, you have the global coordinate system, em.gcs, which is just, you know, axis 1, 0, 0, etc. And you can also make your own. So you can do coordinate system. And you can define your axes in the way that you want. You can put it anywhere. And so an XY polygon has many ways to create these polygons. In the PCB class, you can also add your own polygons. And you can eventually do something like extrude also to give them a thickness. So yeah, I would definitely recommend to just click through and see what functions are available. Mostly there are some that allow you to sort of add features to it. So there's a method to just automatically make a circle, a rectangle, but also a parametric line, and you sort of keep adding these to it. You can actually see it in the Vivaldi example. There I use it as well. And the PCB class, which I'm going to show you now, is a way to create PCB routings. So I'm just going to do PCB.new, and I'm going to start to 0, 0. The width is W2 divided by millimeters because I have all my dimensions in millimeters and I need them here unitless. Direction is in the positive Y direction, and it's just on top. And then I'm going to go straight by an amount that is, I have to look here, that's h, oh, it's actually also not indicate 2 plus h3. It's annoying that I didn't do this. Then I'm gonna turn minus 45 degrees, coordinate type is square, I like that, and then straight by, I don't know, 5 millimeters. And then what I'm going to do is I'm going to say trace is PCB compile paths. So this is going to make all the traces that you scheduled this way. Oh wait, DLFR4. Sorry. Oh yeah, I had to put it somewhere. Okay, the 5 millimeters was quite a lot, and it has to go to the right. I'm sorry. So this is, oh yeah, the L8 plus W2 divided by 2 divided by millimeters. Should have done this not in millimeters, but there we go. And then much shorter, so maybe only 2, something like that. That's roughly what's in the image. Very nice. So I actually don't know if they feed it to the left or to the bottom here in this example. But one thing I can do, so first let me make one thing out of this. So I can do my method is pm.unite. I'm going to do block 1, block 2, block 3, block 4, block 5, block 6, block 7, GL, GR, and trace. And I'm going to set material.lib.back. I think did I screw something up? Oh my god. Sorry, I'm working off a local version. I might have screwed up some functions. I'm sorry. Embarrassing. What did I do? Oh boy, sorry. I think oh no. Oh, sorry. Merge. Trace is a list of objects. It's not an object. It should work. There we go. So now it's one smooth geometry. Good. What time are we? 30 minutes in. I really hope that this is going to work. No chats. All right. So let's add a dielectric box for this trace to live on. So a dielectric is pm.geo.box. So in the PCB class, there's a way to automatically generate this PCB. I'm not going to use it because I've generated all these polygons manually anyway. So this is going to be something like, what was it? WGL plus WGR plus some extra 5 millimeters, something like that. And then it's, what is this? What did I pick? LG plus some extra distance plus, what is it? H1 plus W1 plus W1 plus, this one is defined, H9. And then the box we're going to move, oh crap, minus WGL minus LG minus thickness. You can set material am.lib.fr4. This not doing anything yet, but it will be eventually. I forgot the height. I'm sorry. So there is the box around it. Maybe just remove the 5 millimeters. We'll keep it like this one. Give it a little bit extra margin. I like to give it some space. That seems fine. So this thing works at, I'll consider my modeling done for now and just progress a little bit. This thing is made at what frequency again? Where is the plot? It's 2.4 gigahertz, and it's simulated here from 2 to 3. So I'm going to hope we can recreate those results. Let's make this a little bit smaller. So if you're done modeling, you just do sim.commit geometry, and then you're saying I'm done, and then Emerge is going to do some preparatory work. Then we have, before we can make a mesh, we have to set the frequency. Set frequency range, and we're going to go from 2 gigahertz till 3 gigahertz, and let's start with 21 steps for now. And then we can do sim.generate mesh, and then we can do sim.view. And we need the frequency range because Emerge needs to know how fine to mesh it at a minimum in order to abide by certain quality constraints that if you have too coarse a mesh, you literally can't solve it. And boom, there you go. Now you get this window. This is the PyVista enabled window, and you can see the PCB. So if we want to simulate this, we're going to actually have to add an air box around this. Oh, that's really nice. So let's add that air box here. You can see air is in the geo.box. Crap, you have to pick something smart here. Let's just try something. 30, 40 millimeters, 20 millimeters. In LG. I'm just going to check how big this is. It needs to be a bit wider. 80, 40. One side of the ground plane is, yeah, we have to do something about that. That's true. Oh, that's the wrong dimension. Shit. That is a good observation. 50, 25 maybe? It's probably going to resonate now, so I might have to short it, but I don't want it to. First close this before it can rerun. I'm not too familiar with these, and I think if I should give it some more margin. Oh, this is exactly the size. Well, let's just push this back a little bit. Is this too much? And give it some extra. Okay, this is a bit too much. I think we're going to short it all the way in the back because I don't know how much. I have to keep some distance here in order to not short this contact here. So let's add that. Okay, XY plate. This is going to be, what gap did I use? L8 plus W2 plus 2 times L8, 3 millimeters, 0 means 8 millimeters. Add it to the list here. Oh, maybe a bit more back, further back. Oh yeah, this should have been much. Oh, I'm an idiot. That's fine for now. Ideally, I do this a bit better, but I think this might work. Still, I don't know exactly how they should the port be something like left to right, because they haven't really shown how to connect it in their model. If it connects to a ground that's below this antenna, or if it's excited from the left. Maybe if you know, I might add it to the left here. So we're going to add a port plane, a lump port plane. Port plane, we'll say it's getting a mess. Port plane is going to do XY plate. We're going to make it, this is, what was it? W, shit, where is it? right. 1 millimeter is fine. It could actually be right here. I don't have to do anything. Oh yeah, I have to, sorry. Oh yeah, shit. Come on, no, I don't want you to move that. There we go. I'll put it here. That's fine. So 1 millimeter might be a bit too much. So there's this port surface here. I might have to make it a bit smaller. 0.3. So I think we have the ingredients now. I don't know if this model, I don't think it needs a ground plane. I might have to read about it. I was too lazy. I'm just going to see what happens. I'm not familiar with this model. So let's add the boundary conditions to make this run. So we've generated the mesh. The first one is, so the boundary conditions are in sim.mw is the microwave 3D class that manages all the physics. Then we go BC for the boundary conditions, and then we say lumped, port. And here we add the phase, so it's the port plane that we just added. The port number is going to be 1. The width of the port is the dimension in which the current or the voltage is not applied. So in this case, it's that, what is it? That small 0.3 millimeters. The height is the distance across the gap, which is LA. And then the direction is, in this case, it was the positive x direction, I think. So this would be the m.x axis. You can make your own as well. Let's just check for sure. That's the positive x direction, yes. And then the other arguments are the impedance, but that was 50 ohm, that's the default. So the rest, it says power is 1 and the rest is impedance. And then the airbox is going to be sim.bc.absorbing boundary. This is going to absorb the radiation that's going to escape. And so we're going to have to select the boundary of our airbox, which we can do with air.boundary. If you want to know, did we do our job well, we can do here. In view, we can say BC is true, and that will say boundary conditions, will show the boundary conditions. Whoop, we get this. And so what you're going to see, it picked the absorbing boundaries for the outside. It added a lump port here, and it automatically made every surface that's assigned to pack material back, as you can see. So this is set up correctly. So in theory, we're ready to solve. So what I can do, I can also see our mesh, because this might be an issue. Plot mesh true. We can have it show our mesh. So this is not at all going to work. This is way too coarse. So there are two solutions. We can make our mesh finer manually, or we can use adaptive mesh refinement, which I'm going to do eventually. But one way to make it finer, some personal control might be useful. So after you set the frequency, we can go sim.measure. So this is the class that manages the mesh creation. Set boundary size. And we're going to do our metal. And then we're going to set it to 1 millimeter. So metal was this united metal surface. If we run this, what you can see is that it took the entire boundary, so the perimeter of my surface, and it imposed a size constraint there. But it's also doing this edge here. So if we really want the field to be refined only where we need it, we're going to have to use adaptive mesh refinement, which I can show you in a bit. But this might be a first initial decent guess. Let's see if, I don't think I have any chats, no. Oh, I've not looked at this card. Oh. Check reference for the application where I think that they have a much larger ground plane with the antenna in the corner. Yeah, probably. Yeah, because this is pretty small, right? I just read your comment. Let's see, how many people do we have for? So yeah, I'm gonna see, maybe I have to make it much bigger. Let's see if it works like this. But I know that the ground plane, I'm not that expert on these antennas myself, but I think that it's quite a big part of the total functioning, right? So let's just simulate it first. Data is sim.mw, so microwave.run sweep. So we'll just keep it default here. Now I want to see my S parameter. So I made some plot function for you. import emerge, sorry, from emerge.plot import plot sp, and I'll do Smith as well. So I'll get into details later. Why is this not by default in emerge? Because if it was, then you would automatically be loading matplotlib, and it can be a bit slow to start up, and it's already a pretty hefty library. So that's why I made it an optional import. Is absorbing boundary the same as PML? Nope, it's not. So absorbing boundary is literally a mathematical boundary condition that the first order is basically a surface impedance. So it's like a resistance that's matched with air. It works at one, so it's optimized for one normal incident propagation constant. And in this case, it's a second order boundary condition. So there's some correction terms. PML is actually not a boundary condition. A PML is essentially a layer with a directionally increasing electric conductivity, a low one, but also a magnetic one. So it's like a virtual material. And by adding both an electric and a magnetic conductivity in the right way, so it's actually like you have a loss tangent on your magnetic permeability, you can still keep it theoretically perfectly matched to 50 ohm. And so it's actually more so creating extra surface area or extra volume space for this energy to be absorbed in. I'm not using it now because it just makes the simulation a bit slower and I want it to go faster. But for something so proximate, you ideally want to use PMLs. And for now, the only way to really do it in emerge yet is you have the em.geo.pml box. So this is basically making an XYZ oriented box. And you can say how thick you want the borders, and it will add, it will essentially add these PML layers on the tops and on the sides. And you can say top is true, then it will add one on the top. And if you say left is true as well, then we'll do the top and the left, but also the top left edge, etc. So the PML box is sort of a way, and then it returns, as you can see here, it returns a whole list of all your volumes. But it's a bit slower, so I will do it like this. So these are two convenient plot functions that I make. So what we can do now is, so data, if you look at the type here, what it returns, it's a microwave simulation data object. So it's like a container of all my simulation data. And it's not sorted. So in this case, I have just a frequency sweep, but you might also have two parameter sweeps at the same time, which gives you this 3D data set. So emerge by default doesn't grid out your data, because if you're doing an optimization sweep, for example, it's not really structured. But if you know that it is, you can go, you can ask it to structure it. So in emerge, there's two types of data. There is data.field, which contains literally the electromagnetic field in 3D space, and scalar, which contains all quantities like the S parameters, the normal propagation constant, etc. So what we're going to need is the S parameters, which are in scalar. And so we're going to do gridded. Data is data.scalar.grid. And what this will do is we'll go through all the data that it has and just identify all the axes for the data that might exist, and essentially make a container that has your S parameters, your port impedances, everything that we'll add in the future as well in an n-dimensional data set. So it's an extra step here, but it's sort of a necessary evil in case of parameter sweep where you have this n-dimensional data. And then I can do plot sp, gridded data, and we have frequency here, and gridded data dot s11. And we're going to run it and see what happens. I hope this doesn't take forever. 3 seconds per iteration, so I might have to speed that up a bit. So if anyone has questions at this point, this might be a good time. I'm going to show you how I can parallelize this later, because this is going to take a long time if I have to do it. By the way, for anyone who's in, actually everybody, if you want to do large frequency sweep, I can highly recommend trying to install UMFPAC. It's easier on Mac OS than on Windows. Windows is quite annoying. There's a manual in the resources section on my website. It's quite annoying to install because you have to use Conda, but it's really fast on one core. So you can, if you have 10 cores, you can make them all work in parallel, although it really stops being effective after 4 or 5. But I'll show you how fast this can go later on these MacBook chips. Broop. Well, so that didn't really work. So let's plot some fields. I think probably my short is way too close. First, let's make this a bit faster. So because unfback, there's an explanation in the manual. If I want to parallelize unfback, I need to do something called entry point protection, which basically means that if Python imports this main script as if it's a module, it's not actually going to run it. It's just something you have to do to make parallel processing work. So we do if name is main, and we're going to, oh god, I hate this. I always do this. Main. We're going to call our function, which is going to name it main for simplicity. We're going to say def main. So what this does basically is, if you import a module, it's doing the exact same thing as it is when you run a script. So if you start to do parallel processing in a minute, each new parallel thread is going to run this simulation file as well. And if you don't do this, it's going to actually execute all this code and spawn more. You get this recursive infinite increase of processes, and it's going to grow and blow up your RAM memory. So you have to prevent that this will only be run if I press run here, and all the new threads are not actually going to run this main script. It's something in how Python works. I can't really help it, sadly. But now I can do in run sweep, I can do parallel true. I can say 6 workers, and I can do multi-processing is true. That will activate the multi-processing. If you set this to false, the only way it can do it is with superlu, another solver, and it's much slower. So now we'll do it like this. So it's pre-assembling, running 6 unpacks. So you can see there was about, 3 seconds. It's going to take 5 seconds now, but I'm doing 6 at the same time. So it's on net, it's much faster. So first, let's take this block here and put it even lower, all the way down to LP, right? Boom, and it's done. See? But I'm going to have to waste my time again. Actually, I'm going to set this boundary size a bit coarser to give myself some space. It will shift the frequencies at which it's resonating a bit by being less accurate, but it's going to save me a lot of time right now. So for quick studies, I put the resolution fairly coarse. Oh my god. Okay, so I actually screwed this up. So let's see. This is a good opportunity to see what's going on. So I'm going to plot my simulation and actually see what the fields are doing. So I'm going to do my field. So what I'm going to do is I'm going to extract the E field at a desired frequency. So I'm going to pick, what was it again? Where do I have it here? What is it? It should resonate at 2.4 gigahertz. I'm going to say field is data.field.find. Frequency is 2.4 gigahertz. So it's going to take whichever simulation frequency I had, which in this case is exactly 2.4, and that will be my field. So this is sort of like a holder now of the specific solution at 2.4 gigahertz. So I'm going to do my sim.display. This is, I'm going to create my own plot. And I'm going to do add objects, sorry. I'm going to add all the objects that I have, which is sim.allGeos. So this function returns a list of all my geometries, and I'm going to unpack that immediately to this function. This is called list comprehensions in Python. It's also in the manual. Then I'm going to add a cut plane slightly below my copper trace. So I'm going to do which field should I plot? I should plot all of them. Display, add a surface. I'm going to do my field solution. So what I'm going to plot, this is also explained in my manual. It's a bit of a weird syntax, but it works. Field.cut plane. I'm going to make a cut plane with a 1 millimeter resolution at z equals minus the thickness. And I'm going to plot a scalar field, which is going to be my I think I'm gonna have to settle with norm E, I think is the, norm E. And I'm going to do sim.display.show. So I'm going to plot my normal E field, so just the amplitude. And see what happens. I actually don't have to simulate all these other frequencies, I can just do one. It's fairly quick. There we go. So I have this plot now. Oh, I think this is resonating here now. And this might be... I actually don't know if this port excitation is correct. And I'm not sure if am I supposed to ground this? Rasmus, if you're, if you have a good suggestion on how to fix this, I don't know. This should be much larger. Maybe this should be much larger. Oh boy. Oh yeah, 20 millimeters is nothing. This thing's actually pretty small. This airbox is actually also really close, right, for this frequency band. Is this gonna work? No, this has to be way 100. Oh my god. Rasmus is coming to the rescue. I'm so unfamiliar with these antennas. Oh, I actually don't know if I made this correct. Let's open out a little bit. Oh, good. I always do this. Why am I like this? Oh god. This should be maybe 100. I just want to see. Yeah, but it should work at, so Paul's saying that it's resonating at a low frequency, but we could start simulation from 0.9 gigahertz. That's true. Oh my god, this is going to be hilarious. It's such a bad design. But the manual says it should operate at 2.4. So I think the short that I added is too close to it, and it's shorting the feed point with the other. Should that matter though? No, it shouldn't. No, it shouldn't matter. Damn it, it couldn't be it. Shoot the other ground plane. There we go. Oh, I don't know. I've actually created this artificially now. Make a larger ground plane so you don't make that slot. Yeah, I think so. It's weird because they have this in the menu. Actually, don't know because it's drawn as a floating ground. Is it supposed to be? Make one larger solid ground. You don't have to create that slot. But should it be connected to the right side? That's what I'm wondering. Easily get the field versus frequency rather than having to iterate through every frequency using find. So you get the results of find, but have an additional access that. What you mean, like, so if I understand your question correctly, Jeff, there is not really. So I think you mean that you have this sort of 4-dimensional data set, which is like a 3-dimensional data set or like a cut plane plus the frequency axis as an extra dimension. Yeah, no, there's not. You have to do that manually. It would be too. Yeah, it's gain versus frequency plots. No, I think it's easier to just manually program that. Yeah, I'll make a wrapper, make some function that automates that. That's the best way. I want to keep this sort of the bare functionality as simple as possible, and then make post-processing things to make it easier. Actually, already time. No, I'm gonna finish this. I'm so close. I'm looking at your PCB image. So what I'm sort of thinking. So right now, right? So help me out. I'm too stupid for this. So now I have this very long slot. So should this right side, in your opinion, be connected to the left side? That's the question. And if so, how close? Or should it just be, or do you mean just connected to the right and then at the feed point here, so that it sort of vertically feeds along the y direction? Might that be it? That's probably the best bet. I knew it. I'm so smart. No, just kidding. Okay, so we're gonna do that. I like that idea. Let's take, so we're gonna ground right. We're gonna remove that. WL plus WGR plus 5 millimeters. And then we're gonna take our feed point and we're gonna move it up north a little bit. So a new trace now starts at 0. So we're gonna make it start at 0.5 millimeters. And then this port plane is going to be W, what is it? 2. And the depth is going to be 0.5 millimeters. And the position is going to be, what was it? L8. No. And then this is going to have to change. So this will go to, the width is now W2, 0.5 millimeters, and this is going to be in the y-axis, because we have to specify in which direction it has to impress this voltage. Oh yeah, there's no GR. I hope this works. That would be dope. There we go. There we go. Good job, guys. Oh my god, this looks so horrible. Okay, this PCB can. Okay, so I have to do this a bit more carefully. Okay, so this air box is needlessly large. Let's make this 80 and a bit wider. Might as well, right? So this, I would do this more carefully, but I want to hurry up a little bit so that you guys can see the other picture. And I'll show you very quickly how to do adaptive mesh refinement, because that's really convenient for these structures. It's a bit slow because of how I have to interact with GMSH, but it's hopefully good enough. There we go. I like it. Very good. Okay, show you adaptive mesh refinement, last bit. So to get adaptive mesh refinement, we're going to have to, it's a beta version now, so it's in simulation beta. That's where the extra functionality is in. We're going to, for convenience sake, remove this mesh constraint and do it all manually. So we're going to go, before we run our simulation, we're going to go sim.view plot mesh true, volume mesh false. So we're going to plot only the mesh on the surface. Then we're going to go sim.adaptive mesh refinement. We'll keep the default setting for now. We can say frequency is 2.4 gigahertz. We can pick any frequency here, and then we're going to view it again to see the results. You can also do here show mesh true, then it will show the mesh in each intermediate step. It's going to take a while. So this is our initial mesh, which is going to be horizontal, and then we're going to see what happens. And I think it's probably going to struggle to converge within these steps. Oh, there we go. It's actually already done. I'm so good. And as you can see, it has a finer mesh resolution here. And we can plot our results. And as you can see, it's lightning fast now because we have an optimized mesh only there where we need it. I'm a master. With you guys' help, that's the best part of it. So good. Should we make a far field plot? I should finish with that, right? Might as well show you. to make some slices. Okay, we're gonna make some cut planes. So I'm gonna import a, do we have a far field plot here? They're all polar diagrams, right? So we're gonna see how similar they are. I'm gonna compare them back to back. So we're going to import plot far field polar. And we're going to do some polar diagrams. These are at 2.45 gigahertz. So we're going to go for our polar plots. We're going to do them here. First, we're going to take the field. Field is data. Field dot find. Field is 2.45 gigahertz. Now we're going to have to create the data for the far field plot from this. We're going to derive it. The way we do it is we say, so actually we can take multiple slices, 3. So we're going to do far field 1 first. We're going to do field with, and then on our field we're going to call far field 2D. The reference direction is going to first be, what is it? First we're going to go with we can go em dot x-axis, and then the plane normal we're going to pick z axis. The faces are going to be air dot boundary. That's what we want to integrate over to extrapolate the fields outward. Angle range, we'll do minus 180, 201 points. This is all looking fine. We'll create some more. This is going to be in the, actually we need more. The x direction. So this is in the z-axis. So then the y-axis, and this is, what's the last one? So we have x. I'm tired, that's it. So x1, we have this one. Oh, we have x is the normal, and then we'll take whatever, z. To far field, and then we go plot far field polar, and so we need the angles first, and that's conveniently put in f of 1 dot angles, and then the field that we're going to plot is what they have in their document is, I'm going to show you what I'm looking at. We're going to recreate these plots. XY plane. Is this gain in dB? It doesn't even say, right? That sucks. Oh, 2 dB per diff. So that would probably be gain. We're going to go for gain. So we do f of 1 dot norm E, so the absolute E field, and we're going to divide by, actually I think we need to. We can go here. We can say in dB is true. We're going to put the dB floor, because working rate at dBs can go to minus infinity, so we have to put some cutoff level for the vertical axis. Where did I put? So this, in their case, is, they don't have a floor. dB floor minus 10. Yes, thank you. I think I have a function here that says, if I remember correctly, no. Okay, well, then we're going to do it ourselves. So to get the gain, we divide by em.lib.a ISO. So this is the amplitude for an isotropic radiator. Now we can do all of these. There we go. It's going to crunch through it again. So there's also, just an FYI, there's a way that I can show you very quickly to save all this calculation work so that you can do your post-processing and not have to rerun your model every time. Oh, this Z radius is probably way too close. That's cool. So let's see if we can recognize some of these. So realistically, this is going to depend really on how you generate your, I think these are probably the same here. So this would be the XZ plane, and the second one that I have is the XY plane. The first was XZ. So this would be XY. It's probably really going to depend on the shape of your ground plane, honestly. So a small chance that these are going to look alike, unless I know exactly. But there's this minimum radius. So this, if this isn't dB, then there's some minimum dB level that's at 0, and it doesn't actually tell me what that is, which is pretty sloppy because there's actually not really. Reference level is 1.1 dBm, so minus 30. Okay. So I'm going to do once more. So I'm going to show you very quickly how you can set up so that you don't have to rerun this every time you want to simulate again. So I think I would personally probably converge an extra step just to make sure that it's well converged, but still not. dB4 is minus 30, right? Why is this minus 17? Oh, did I screw something up? No, did I break my functions? All right, I screwed something up somewhere. I hate this when this happens. Okay, so very quickly, especially if you're on macOS, so I can show it right here. If you have a Linux-based operating system, you can do this. Emerge new, my project, my file, and it will create this folder for you. And in that folder, you'll have your data and two files. You have a simulation file with some defaults in there, here, and you have a post-processing file. So if we look at the simulation file, it has this nice with statement, which what this does for Python is it will execute the code here. And if it stops for any reason, including a crash, it will always execute some closing code. And in this case, that's saving your project. So no matter what happens, this will save whatever data it has to your hard drive because of this, what we call a context manager. So this is a basic rectangular waveguide simulation setup. So I can run this. It will run very fast because it's a very simple simulation. And then in post, so here I have save file is true. As you see, it's called my file. It will have this myfile.data directory, EM results. And it's in here. And so if I go post, I have a load file is true. And if I run this, I have my S parameters and the field. And so the data that your simulation created here by doing run sweep, you can find that now in basically your model here. It's just named M. So m.data.mw. That is the data that we were referencing earlier, right? So this here is what gets spit out by this function here. So this literally, what this returns, it says it here, is an MW data object. And that's what this is, MW data. It's the same thing. So this way, it's also explained in the manual, you can actually separate running from post-processing. And because each simulation might have a different mesh, if you have a parameter sweep, you can say m.activate. And then here, if you run it for some variables, it might be theta is 45. It will look for whatever iteration you had with theta 45 and will show you the geometry corresponding to that. It's explained more in the manual. So yeah, that's it. If I'll extend this by half an hour. If anyone has a question, something they would like to talk about, something they would like me to demonstrate, then please, by all means. I'll host this code on my website, by the way, so you guys can look at it. Under the stream, I'll probably make a blog article where I put the document from Texas Instruments and this document so you guys can play around with it as well, and probably improve on it, because this, as Rasmus pointed out, there's probably a better way to simulate this with a more realistic ground plane, but it's just to show, how you set it up and how you go through the steps. For the F antenna, yes. So yeah, very good ones. Oh, that's actually something I haven't discussed. So really cool. So I've simulated this at 21 frequencies. there's something you can do called vector fitting, which you might have heard of, which basically means using physics to figure out what poles and zeros in the transfer function correspond to that function. I didn't create that. I credited someone else who wrote this script. I just stole it, which was allowed with proper accreditation, which means that I can create a denser frequency space and then show my parameters there. So what I will do is the following. I created this Smith plot here. So I can do Smith, and I can do here my gridded data. And here I plot a list of the S parameters. It's a bit weird because in principle you only need to plot your S11. So I'll do S11. And I can optionally add my frequency axis. I will say F is gridded data dot freq. This will just draw sort of the text of the frequency labels. What I can also do is this. I will show that here. I can do F dense is gridded data dot dense F. So this is just a convenient function to generate 1001 points in the same frequency range as what I simulated, but it's by S and P. I can also just do whatever interpolation you want. I can also say numpy.lin space 2 gigahertz, 3 gigahertz, 2001. It doesn't really matter. That's just a convenient function, so you don't have to import numpy. And then what I can do is smith dot gridded data, and I can do model S. And so here I provide again the S parameter, but also the frequency grid. And it will, instead of giving you the S, it will give you the interpolated S. And then for F, I can do F dense. I can show you what this would look like. You can also export to touchstone, and I'm going to add soon a function to also de-embed for some distances. But you can use the normal numpy arrays to do it manually as well, if you know the functions from the top of your mind. There we go. So this is the normal plot. As you can see at these labels, you can decide yourself here. There's some argument that defines how many of these frequency labels are added, but you can see that it takes these steps. As you can see, it's blocky. And the model S has this smooth curve. And actually, because it's like this, I think you only need to simulate it at 3 frequencies to derive this curve here. So you could do with 3. I can actually show that here. I can actually also show what it looks like there. Oh, I can hate that I broke that function. I don't know how I did that. Plot SP, grid F dense, and then gridded data model S11 dense. You can also add labels here and do all kinds of other fancy stuff if you want to. So I'm going to show, I think I'm going to go, it should work with 3. Let's see. So, course, boom. Course, how does it do it? So now, because we know it's a very simple single resonant function in this frequency domain, it can derive this, but it could be very useful. Because I don't have the frequency, so I picked 2.5 now for these plots. And the field. Also, for people who want to know, I can also, I knew you might like this. Now I'm plotting the normal E field, so it's like the absolute value. I can also pick EY in this case, so the YE field, and then I'm going not for the imaginary part, not for the real part or absolute, but for the complex value part. Because I need this if I want to do animate. All I have to do is just first call animate, and then it will say whatever plot function I'm going to do next, I'm going to animate that one. In this case, it's taking 35 steps. Oh, oops, I want to do something. Okay, so because we're plotting the field amplitude, it's going to go to plus whatever value minus. We want to symmetrize our color plot so that we have sort of like this, I'll show you, I have this custom color bar that goes as like red colors for positive fields and blue colors for negative fields, and it works better. So I'm going to show you. I think I'm going to go, it should work with 3. Let's see. So now because it's, we know it's a very simple single resonant function in this frequency domain, it can derive this. But like gain and S1 pixels. So I don't have a function that plots like cut files. I don't know if there's a standard format. For the S parameters, I'll show you in a second. Boom, boom, boom. There we go. And you can see this animation. You can see it's transparent even in 0. So it's this custom color plot. And very important here, you have to press Q to close. It's a very annoying thing. If you cross it here, some shadow process will keep running and it will hold your terminal and you can't run new simulation. Very annoying. I have looked at it. I spent days trying to figure it out. You have to press Q. That's the only way to do it. To export files. So what you can do to export is say gridded data dot I think export touchdown. You can pick a file name. You can pick a different reference impedance to normalize it to, and the format, or some custom comments. So that's the my file. What you can also do, I've added that in. I don't know if it's uploaded in the latest version yet, but what you can also do is import touchstone data if you want to superimpose it in a plot. I think you can do em.lib. Wow, where did I put it? Touchstone data, there we go. File name. And then this object you have your F, your frequency axis, and then you can also do 1, and you can also plot touchstone data if you want to superimpose it for some reason. But yeah, this should create the data file for you. I can actually see if it works in this one. And the data and scalar grid export touchstone test file. Test B. I think you don't even need to add the extension. Let's see. Because it may be a bit more interesting. So this is halted by this plot window. There we go, test file S2P, and there you have your S parameter data. So that's that. So if people have more questions, you can ask them. Otherwise, I'm going to close off for today. Curious how big this file is going to be for this. And by the way, for exporting, in case you want to know, you can also do m.export. And then you can do my geometry.step, and you can export step files. And these files are all supported. This is all. I'm just calling a GMSH function, so don't thank me for this. But you can also export your geometry. You're welcome. Thank you. Yeah, welcome. Just wait a bit more. I missed the first 30 minutes. I assume you can also simulate 3D models. Yes. Good question, Renier. So I mentioned this in the first 30 minutes as well. The best way to do that is importing step files. And there's what you can find on the GitHub, but also on my website. There's the example packs. And then there's demo 17 shows how to import a step file. And basically, I will show it very quickly once more here. Right, I probably have it in my I lost here. So this is happens to be the file. So the way you roughly do it is like this. You go em, so emerge.geo.step items, and you have to give a name. This will be used to name all the different elements that you're importing in an emerge language. So, oops, sorry. Yeah, this is just you have to type the file path. This is just this extra work is just to make sure that it will look in whatever directory this example was put in. Otherwise, you get annoying parts where people put the directory in the subdirectory. They're not in that directory when running the script, and they get errors. So this is just to keep it together. And very important, some units. Sometimes the millimeter unit doesn't get imported automatically, and you get this thing that's 1,000 times too large. So you can set the unit here. And you have this step object. And inside the step object, all the 3D, 2D, and 1D objects and surfaces and points are stored. So in this case, for this step file that I created, if you go to step.volumes, which is a list of all the volumes, you will find 3 objects in this case, which is flange, and I call it flange air cutout, and the electric rod here. If you don't know like in what order are the volumes returned, what is actually being produced, the moment you call this, the objects exist. So what you can do, and this might be interesting to show, I can maybe even open it very quickly here. Open, save, it's fine. I'll go here. So let's say you don't know what happened and what got imported. So you have to first measure geometry, and then you can do view labels as true. And if you run it, so I'll show you what this geometry creates here. Oh my God, I automized something, sorry, just take a while. You'll see that it has labeled these objects. So you'll have dielectric rod object 0 here, and it says dielectric rod object 2. So that's sort of the order in which they're added. So this can be a way to temporarily see, okay, how are these geometries named? It might take something. So there is a labeling system in step files that if you create them, they'll have a name, but for some reason, it doesn't get introduced into the GMSH model that I'm using. So it isn't available to me. So you need to do some finicking around to see which volumes have been created. So what that might mean in practice, what I would do personally. Can I stop this please from continuing? So no. After you do this, let's say this is where you stopped. You just did the step imports. So I'm just going to make sure it quits here. What you can do is print step.volumes, print step.edges, print step.surfaces. And you'll see if you run this, okay, so you have the electric rod object 0, 1, and 2. That's what they're named. And there are no surfaces and edges. So here you have like this overview. So you know, okay, I have to extract from this object 1, object 2, object 3 is step.volumes, and it will unpack these. So this object will be named object 1, etc. And then you can play around with them. So you have to sort of, while going along, figure out what's actually being created in these step files. But yeah, that's how you can import them. And I'm also working on Gerber file imports, so you can also import Gerbers and DXF files very shortly as well. It's pretty nightmarish file formats, but it's getting faster. If that's what you meant by 3D models, by the way, I assume that it's existing files. And for fun, there's also this convenient enclose function that allows you to wrap everything inside this box that your step file has. If the answer was more generally, can you model 3D structures? Yeah, absolutely. You can do horns, you can do waveguide filters, you can do whatever you want. This is just an antenna geometry that I picked for now. We could have also given the traces that we just created thickness physically, and then that way you can model copper losses as well. Doesn't work on 2D surfaces yet. It's almost time. I'm gonna call it quits at 9:30. So if there's any last burners. Oh yeah, it might take a while to get into. Yeah, I definitely recommend just checking the tutorials. I try to put as many comments in there to explain sort of what's being done. Yeah, I just have to play around with it, I guess. How much RAM is used for the simulations? That's a good question. It's unpredictable how much RAM will be used. In practice, it depends on the mesh size. The reason being that you have this sparse matrix, and so, for example, if you have a very flat geometry with say 50,000 tetrahedrons, you might need less memory than if you have a spherical geometry. This is something to do with how these direct solvers use. Typically, so during solving, that's what will dominate it. It's hard to say. I think if you have about, so let's see if we can very quickly run something simple here. Yeah, if you have a model that has about 30,000 tetrahedrons in that ballpark, 50,000, you might be looking at about a gigabyte of RAM memory per frequency that you're running in parallel. So if you have 4 in parallel, that would be 4 gigabytes, something in that ballpark temporarily. But then after it's done simulating, we'll clear up that memory and restart again. So that's just what it needs to solve it. It's not actually how big the data set is, but you have this sparse matrix, which is basically an n by n matrix that's 99.99% empty. It's all zero, so you only store the non-zero entries. But then when it's doing what's called an LU decomposition, those lower and upper triangular matrices have fill-in, so they become massive and they start to get filled with a lot of terms, and those will push your RAM memory up quite a lot. So yeah, it can go up to a couple of gigabytes per frequency. You have to experiment with it because it's really hard to predict how much RAM is actually being needed during solving. I think for this one that we just made, it's not going to be more than a couple 100 megabytes. And maybe something interesting to mention. So what emerge does, if you run parallel sweeps, it will pre-compile all the matrices. If you do frequency sweep, that's like 200 frequencies long, and it will pre-compile all of them. That can add up. A fairly big model might take about 100 to 200 megabytes of the assembled matrix, so it's much smaller, not the gigabytes. But you can constrain how many will be pre-assembled in here. If you do true 4, you have this frequency groups arguments, also explained in the manual, where you can say how many, in this case, 8 matrices or frequencies will be assembled, then those will be solved in parallel, and then when they're done, it will assemble another 8, and then we'll send those out to be solved. So that's sort of a way to group it, because otherwise, if you do like a frequency sweep of 100, people have had their computers crash, because it's just stuffing your PC full with an insane amount of data. So I see it's 9:30. So thank you, 3-4 people. That was about it for joining. I guess I will do this another time with some other requests. So if people feel like I really want this to be discussed, then we can do that. So ciao, everybody. Have a good evening or a good day if you're in a different part of the world, and I'll speak to you later. Thank you.